All right. So we have this problem here, question 3 of the study guide. And I'm going to call this a unit step second order circuit. The reason being is we have this U of t here. And what that means is, what it directly correlates to is for t less than 0, U of t, this function, is equal to 0. U of t for 0 greater than t, it's equal to 1. Now, it's important to notice that this directly substitute into this, by the way. U of t is for t less than 0. 0, this becomes 8, negative 8. And then 1 makes it negative 6. Anyways, it's good to notice that there's also the variant negative t. And all this means is that these are switched. For t less than 0, it becomes now 1. And for t greater than 0, it now becomes 0. That is for this. Okay. Now that we know this, we can solve it. Okay. So, our goals are to find the initial conditions for the capacitor and inductor. Let's first do that. And we also need to solve for as it goes to infinity in its transient state. And we will do that. So for t less than 0, I solved it earlier. Let's do this. For t less than 0, right, we know that U of t is going to be 0. So negative 8 plus 0 is negative 8 volts. Okay, so it starts at negative 8. So, and the inductor is replaced by a short circuit, and the capacitor is replaced by an open circuit, because they've sat for a very long time, and that is what they're going to behave as when they sit for long periods of time. So now, we need to find the value for the capacitor and inductor. The capacitor is simply from this point to this point, the voltage across this resistor, because we can see that the shortest path from A to B is as follows, right? And B being ground. So, it goes past that one resistor. Okay. Now, let's see. Let's figure out the values then. So, those values will be simply negative 8 divided by 15. Let me pull up the calculator first. It's going to be negative 8 divided by 15 will be equal to V is equal to R times I. This will be the initial current plus the inductor. All right. So that is going to be negative 0.533 going that way. Okay, and that times 15 is negative 8. So all of the voltage goes to the capacitor. A simple reasoning behind that is that there's one resistor, so there's nothing really splitting up the voltage. Okay. Found our initial conditions. We must also note that when we try to find later on dV for 0 plus dt, this is for the first derivative initial condition. I will explain this in great detail, right? But when we get there, I will bring it back up. Okay. So now we need to solve as the circuit goes to infinity. So as this circuit goes to infinity, VC of infinity. We need to find the voltage as it goes to infinity. Well, now we have -6 because now U of t is equal to 1 for greater than 0. And since that's the case, we get -6. And we get a new voltage, which comes out to be -6 as the final value. Because there's only one resistor. You can figure that out doing whatever method you prefer. But since there's one resistor, it will be -6. And since as it goes to infinity, this will be a short and this is an open. Okay, now for our last part, we need to figure out the transient state for this circuit. Let's erase all this circuit. So, since these are not directly in series, this is a parallel, which means 1 over 2 RC is equal to alpha, and 1 over root LC is equal to wumbo. And the formula as follows. Plug in this into this equation, and you should get your answers. So 1 over 2 RC, 2 times the resistance, well, there's only one resistor, so there's 15, times the capacitance, 5 times 10 raised to -3, and we get 6.66, and wumbo will be 6 times 10 raised to the -3 times 5 times 10 raised to the -3, square root of that number, 1 divided by that, 182.57, and we plug in our values, and we'll get, let's see, this squared minus this squared, we get, if you plug in your values, you should get 182.45i plus or minus -6.66. Now let's plug this into our characteristic equation. I think that's what it's called. E to the alpha, this is alpha, -6.66. This is a formula from differential equations. C1 cosine of this, 182.45 t plus C2 sine of 182.45 t. Okay, now this is for VC of t. Whoops. Now we must note that what is the final value, right? What is the final value of this circuit? -6. So we must make note that if there is a different final value, if it doesn't go to 0, we need to include that. So it's -6 is the final value it approaches. The only reason you need this is because this whole right side will approach 0. So if your final value isn't 0, it's not going to approach what it needs to. Okay, so now that we've added that, we must now solve our C1 and C2. So initially, where do we start? -8. So plug in our initial conditions, which, if you want a more visual, this is equal to C1 plus C2 plus V final. That's probably like in your textbook. But at t of 0, we must note that sine is going to be 0, so that's going to disappear. C1 at 0, cosine is 1, so we got that C1. And -6 is just chilling, it stays. So if we solve for C1, we get, add the 6 over, -2. Okay. So now we need to figure out what C2 is. How do we do that? Well, we need to find our next initial condition, which is going to be our IVP for dV0 plus the first derivative, dt, of the IVP. Now we'll take the derivative of this function, which is just going to be, we'll do a product rule, -6.66e to -6.66 t C1 cosine 182.45 t plus C2 sine 182.45 t. Okay. Now for the derivative of this here, we get plus e to the -6.66 t. Now we do the inside. Cosine becomes a negative sign, so negative times the inside here. 182.45. C1 sine 182.45 t. Plus, this becomes cosine 182.45 C2 cosine 182.45 t. And there we go. Now what do we do about this? Well, you could simply say, well, the derivative of this, which is -8, is 0. Or, I like doing it this way because this shows you what it actually is. So we know that I is equal to C dV dt. Well, let's make note. I of the capacitance for 0 plus divided by the capacitor is equal to dV0 plus of dt. This is also true when you look at it more deeply. So how do we kind of do this to find our answer? Well, we know the initial, we need to figure out the initial current through the capacitor. And how do we do that? Well, we know that if we go up here that we have initially -0.533. So if we figure out the current going down this way, we can figure out the current going this way. So we know if we do a KCL at that node, -0.533, and then the current going down through this resistor is equal to voltage divided by resistance. The initial voltage will be the capacitor. So we know that the initial voltage is -8 across that capacitor divided by 15. And this is for 0 plus. This is right after this switches to -6. So now I just want to make note that that we know that when we pick for the voltage for this resistor, it's going to be the capacitor, right? Because the capacitor is at this point touching this node up here, and the inductor is separating the voltage source over here on the left. Okay. And we get going down is -0.3. Where was I? Somebody interrupted me. So yeah, so if we do a KCL, right, this current coming in to this node makes it negative, so that's a positive 0.33. The current coming down here is -8 divided by 15, which is a negative 0.533 plus x. We don't know this current this way, so we know those two, so we can solve for it. Subtract the x over. -x, these cancel. It's 0. 0 is equal to x. So in this case, when you solve for it, right, make this look better. This way is the capacitor. this is that resistor, and this is the inductor coming in there. So this one and this one cancel out, and we get 0 going this way initially. So in this case, we get this is 0 after you grab the root. But there are cases where that is not true. Is there? I think there's a case, but you should always make sure that when you check the currents like that they equal to 0. That's how you know 100% that that's the case. So we know that that's 0. So now let's solve for our C1 and C2. So sines disappear, right? Sines are 0, cosines are 1. So we get negative 6.66. This turns to a 1 because it's an e. E to the 0 is 0. C1, cosine is 0, plus, this is a 1. This cosine turns to a 1, so we get plus 182.45 C2. Okay, and we can solve for this. We know what C1 is, so we can just plug that into our calculator. So we will do that. My phone's about to die. No. No. One sec. I need to plug in my phone. Save the phone. Okay, so now let us finish this problem since we're at the end. So negative 6.66 times negative 2. Okay. We'll subtract the... Let me knock out... Oh. My bad. Excuse me. 13.32 equal to 0. Subtract that over. Well, if I sneeze again, I'm going to have to pause real quick. Is equal to 182.45 C2. Divide that over. Hold on, I'm about to sneeze. I think I'm good. Divide that over 182.45. Negative 0.073 is equal to C2. Okay. And we have our values just like that. So now let's plug that in. Voltage across the capacitor as a function of time is equal to negative 6 plus e to the negative 6.66 t. This is negative 2 cosine of 182.45 t. Oh, this is going to look not the best. Minus 0.073 sine of 182.45 t. This doesn't look good written like this, but this is the answer. And you can check that because we can our initial condition is negative 8, right? We start at negative 8. So if we plug in 0, this is 1, cosine is 1, sine is 0, so we get negative 6 plus negative 2 is equal to negative 8. That means we are doing good for the most part. So if you do this on a test, whatever test you have, your professor will give you a lot of credit if your transient state function gives you negative 8 to start with. So yeah, that's how you solve this question.